What if the single greatest mistake in the history of human exploration wasn't a wrong turn, but a wrong assumption? For centuries, we have stared up at the velvet black of the night sky, obsessed with a specific kind of comfort. We looked for reflections of ourselves. We scanned the cosmos for the familiar, for liquid water lapping against rocky shores, for puffy white clouds drifting through nitrogen skies, and most importantly, for the warmth of a sun on our backs. We convinced ourselves that life is a fragile thing that needs a campfire. We drew a line around every star in the galaxy and called it the Goldilocks Zone, telling ourselves that anything outside this narrow band of warmth was too cold, too dark, and too dead to matter. But what if we were looking at the map upside down? What if the most vibrant, promising real estate in the universe isn't basking in the sunlight, but hiding in the dark? There is a revolution happening right now in how we understand our place in the cosmos. It isn't being fought with starships or laser weapons, but with magnetometers and grainy thermal images. It is a quiet shift that has completely dismantled the old rules of biology and physics. We are waking up to the realization that our solar system, and likely the entire galaxy, is not a lonely collection of rocks orbiting a fire. It is an archipelago of hidden oceans. We are finding that the warmth required for life doesn't have to come from a star above. It can come from the crushing rhythmic heartbeat of a world burning from within. Welcome to the frozen curtain. To understand why this shift is so profound, you have to understand the psychological trap we've been stuck in for 400 years. Since Galileo Galilei first pointed his spyglass at Jupiter in 1610, we have been biased by our own biology. We are surface dwellers. We evolved to photosynthesize, to crave the light, to fear the dark. When we imagined aliens, we imagined them like us, walking on a surface, looking up at a sun. This bias dictated our science. When astronomers looked at the outer solar system, at Jupiter, Saturn, and the ice giants beyond, they saw graveyards. They saw temperatures dipping to 300 degrees below zero. They saw radiation belts intense enough to fry electronics in minutes. They saw ice, endless rock-hard ice. The assumption was absolute. These were frozen wastelands. They were preserved snapshots of the early solar system, pristine and beautiful, but utterly static. A dead moon was just a dead moon. It was a ball of ice and rock that had cooled off billions of years ago. There was no reason to look closer for a heartbeat. But the universe has a funny way of waiting until you are absolutely certain of something before proving you completely wrong. The first crack in the facade appeared in 1979. That was the year the Voyager missions conducted their grand tour. Voyager 1 and 2 were the ultimate scouts, hurtling through the darkness to snap the first close-up family photos of our giant neighbors. As they swung past Jupiter, Mission Control expected to see cratered, battered worlds. In a solar system filled with flying debris, everything gets hit. Our own moon is pockmarked with the scars of billions of years of impacts. Callisto, another of Jupiter's moons, looks like a golf ball that's been through a war zone. But then Voyager's cameras swung toward Europa. The images that came back to the Jet Propulsion Laboratory didn't make sense. The scientists were looking at a moon the size of our own, but it looked wrong. It was too bright. It was too smooth. There were no massive craters. There were no mountains. Instead, the surface looked like a shattered eggshell, crisscrossed with thousands of dark, reddish lines that looked like veins. It looked like the Arctic Ocean on Earth, a vast sheet of ice that had been broken apart and refrozen over and over again. In geology, smoothness means youth. A surface without craters is a surface that has been paved over recently. Something was erasing the scars. On a dead world, nothing erases scars. Craters stay there forever. If Europa was smoothing out its own wrinkles, it meant Europa was active. It meant the surface was moving. And if the surface was moving, something beneath that ice had to be lubricating it. The whispers started then. Could it be water? Could there be a slushy layer, or perhaps even a liquid ocean, trapped beneath that frozen shell? It was a radical, almost heretical idea. Water, in the vacuum of space, 500 million miles from the sun. It should be frozen solid as granite. The physics didn't add up. Where was the heat coming from? The sun at that distance is just a bright star, offering no more warmth than a glow stick in a freezer. Without a heat source, there is no liquid water. Without liquid water, there is no life. The math said, Europa should be a solid block of ice. The photos said, Europa was alive. We had to wait nearly 20 years to resolve the paradox. In the mid-1990s, the Galileo spacecraft arrived at Jupiter, designed to orbit the giant and study its moons in detail. It carried a suite of instruments, but the one that would change history was the magnetometer. A magnetometer is essentially a fancy compass. It detects magnetic fields. Jupiter has a massive screaming magnetic field that rotates along with the planet. As the Galileo probe flew past Europa, the team led by physicist Margaret Keevelson noticed something bizarre. Europa was disrupting Jupiter's magnetic field. It wasn't just sitting there. It was reacting. The data showed that Europa was generating a magnetic field of its own, but only when it passed through Jupiter's field. This is called an induced magnetic field. For that to happen, something inside Europa had to be electrically conductive. It had to be a fluid. It had to be moving. Rock isn't conductive enough. Pure fresh water isn't conductive enough. But you know what is? Salt water. Kivelson's team ran the models. The only thing that fit the data, the only thing that could explain the ghostly signal the magnetometer was picking up, was a global shell of salty liquid water, and not just a puddle. The data suggested an ocean up to 60 miles deep, burying the entire moon. If the calculations were right, this tiny moon, smaller than Earth's moon, held twice as much liquid water as all of Earth's oceans combined. Suddenly, the Goldilocks Zone looked like a relic of the past. We had found the largest ocean in the solar system, and it wasn't on a blue planet near the sun. It was wrapped in a parka of ice, orbiting a gas giant in the freezing dark. But the mystery remained. How? How does a moon kept in a celestial freezer maintain a liquid ocean for billions of years? The answer lies in a concept that is both violently destructive and creatively beautiful. Tidal heating. To understand tidal heating, you don't need a degree in astrophysics. You just need a paperclip. Go find a thick wire or a paperclip. Hold it in your hands. It's cold, rigid metal. Now bend it back and forth, fast. Do it 10, 20 times. Touch the bend to your lip. It's hot. It burns. You didn't hold it over a fire. You didn't plug it into a wall. You created that heat through friction. You forced the metal crystals to rub against each other, converting mechanical energy into thermal energy. Now, imagine Europa is that paperclip. And imagine the hand bending it is Jupiter. Jupiter is a gravity monster. It is 318 times more massive than Earth. Its grip on its moons is absolute. As Europa orbits Jupiter, it isn't a perfect circle, it's an ellipse. Sometimes it's closer to the planet, sometimes it's further away. When it's close, Jupiter's gravity stretches the moon, physically pulling it into an egg shape. When it moves away, the moon snaps back into a sphere. This happens every single orbit, every 3.5 days. Stretching, snapping, stretching, snapping. The solid rock and ice of the moon are groaning under the stress. This constant kneading generates massive amounts of internal friction. The core of the moon gets hot. The rock melts into magma. The heat rises, melting the bottom layer of the ice shell, creating a vast, warm, dark ocean that never freezes. This was the aha moment. We realized that habitability doesn't require a star. It requires gravity. It requires a dance. Europa isn't alone. It is locked in a rhythmic resonance with its siblings, Io and Ganymede. They tug on each other, keeping their orbits elliptical, ensuring the squeezing never stops. It is a perpetual motion machine of heat, powered by the sheer mass of the solar system's king. But science is a demanding mistress. Indirect evidence, no matter how compelling, is still just a shadow on the wall. We saw the smooth ice. We detected the magnetic field. We understood the physics of the squeeze, but we had never actually seen the water. We had never touched it. Europa's ocean is locked behind a shell of ice that might be 10 to 15 miles thick. It is a fortress. We needed a smoking gun. And strangely, we didn't find it at Europa. We found it at a tiny, overlooked moon, orbiting Saturn, Enceladus. If Europa was the star of the show, Enceladus was the extra in the background. It is tiny, only 300 miles across. It's roughly the width of Arizona. It's so small that it shouldn't have any heat left. It should be a frozen solid ice cube. When the Cassini spacecraft arrived at Saturn in 2004, nobody expected much from Enceladus. It was just a bright, white pixel. But as Cassini swept through the Saturnian system, its sensors picked up something odd. There was a disturbance in Saturn's magnetic field around Enceladus. The moon was pushing against the planet's magnetosphere. It was leaking something. The mission controllers, led by brilliant minds like Linda Spilker, decided to take a risk. They altered Cassini's trajectory. They sent the probe in for a closer look. What they found turned planetary science on its head. Enceladus wasn't dead. It was erupting. At the south pole of this tiny moon, the camera revealed 4 massive parallel fissures. They looked like claw marks raked across the ice. The scientists called them tiger stripes. And coming out of these stripes were jets, not gentle puffs of steam, but supersonic geysers of water vapor and ice crystals blasting into space at 800 miles per hour. This wasn't a theory anymore. We were looking at it. We were watching a moon vomit its insides out into the void. Enceladus was so active that it was creating an entire ring of Saturn, the E-ring, out of its own exhaust. But Cassini wasn't done. In a move that felt more like an action movie than a science experiment, NASA decided to send the probe into the line of fire. They ordered Cassini to dive directly through the plumes. Imagine the tension in that control room. You are flying a billion-dollar spacecraft, a delicate machine made of foil and silicon, through a cloud of saltwater spray at thousands of miles per hour. But they did it, not once, but multiple times. And as Cassini tasted the spray of Enceladus, its mass spectrometer began to read out the ingredients: water vapor, ice grains, salts, methane, ammonia, carbon dioxide, and then the big one, molecular hydrogen. This was the final piece of the puzzle. Molecular hydrogen is a very specific gas. On Earth, in the deepest parts of our oceans, where tectonic plates pull apart, you find hydrothermal vents. We call them black smokers. Seawater seeps into the cracks, touches the hot magma below, and blasts back up, superheated and laden with minerals. That chemical reaction, rock touching hot water, produces molecular hydrogen. Cassini had tasted the exhaust of a hydrothermal vent. This changed everything. It meant that Enceladus wasn't just a pocket of water trapped in ice. It meant the water was touching rock. It meant there was a seafloor. It meant there was chemistry. Why does this matter? Because for a long time, we thought life required a spark, a lightning strike in a primordial soup, or a bath of UV radiation from the sun. But on Earth, we found entire ecosystems that don't give a damn about the sun. Deep in our own oceans, miles beneath the surface where sunlight has never touched, there are cities of life. Giant tube worms with red plumes, ghost crabs, translucent shrimp. They don't eat plants. They don't need photosynthesis. They are chemotrophs. They eat the chemistry coming out of the vents. They eat the molecular hydrogen. They run on the heat of the Earth itself. If that can happen here, in the crushing dark of the Pacific, why can't it happen there, in the crushing dark of Enceladus or Europa? The realization hit the scientific community like a sledgehammer. We have been searching for Earth 2.0 for decades. We've been looking for blue skies and green grass. But the most common habitat for life in the universe might not be an Earth-like planet. It might be an ice-covered ocean. Think about that. If you were an alien arriving in our solar system and you looked at the biology, you might conclude that Earth is the weird one. Look at those strange creatures, you'd say. They live on the outside of their planet. They are exposed to the vacuum, the radiation, the meteors, the fluctuating weather. How dangerous, how exposed. The creatures of the ice moons would be the safe ones, encased in a 10-mile thick armor of ice, floating in a stable, warm, eternal dark, protected from every cosmic disaster that wipes out surface life. The dinosaurs died because a rock fell from the sky. If there is life on Europa, it wouldn't have even noticed the asteroid that killed the dinosaurs. The ice shell is a shield that has stood for billions of years. This is the frozen curtain. It is not a barrier that stops life. It is a blanket that cradles it. So, where does that leave us? It leaves us standing on the precipice of a new era. The story of the next 50 years of space exploration will not be about planting flags on dry dust. It will be about drilling through the ice. It will be about submarine diplomacy. We have shifted our gaze from the stars to the abyss. The Europa Clipper is on its way, a massive, shielded vessel designed to orbit Jupiter and map the ice of Europa, searching for a spot thin enough to maybe, just maybe, let us in. We are designing robots, cryobots, that use nuclear heat to melt their way down through the shell, trailing fiber optic cables behind them, until they break through the ceiling of that alien ocean and turn on their headlights. Imagine that moment. Imagine the camera descending through miles of white ice, the darkness total, the pressure mounting, and then the ice gives way to black water. The lights flick on. The beam cuts through the void. What will we see? Will we see black smokers churning out nutrients? Will we see microbial mats coating the vents? Or will we see something swimming past the lens? Something that has lived in the dark for 4 billion years, completely unaware that there is a universe of stars above its roof. The Goldilocks Zone was a fairy tale. We told it to ourselves to make us feel special, to make us feel like our specific conditions were the only ones that mattered. But the universe is far more creative than that. It doesn't need a sun to make a home. It just needs gravity, water, and rock. The stage is set. The lights are on. The water is warm. The question is no longer, could life exist there? The question is anyone home? But before we can answer that, we have to understand the sheer scale of the challenge. We have to understand the violence of the environment. To get to these serene, hidden oceans, we have to sail through the most dangerous waters in the solar system. We have to survive the radiation storms of Jupiter. We have to navigate the rings of Saturn. We have to understand the history of the detectives who got us this far. This isn't just a story about ice and water. It's a detective story. It's a story of how we moved from a blurry dot in a telescope to tasting the salt spray of an alien moon. It's the story of how we stopped looking for mirrors and started looking for windows. And it begins with a man who didn't even know what he was looking at. When Galileo Galilei first saw these moons, he called them the Medicean stars. He thought they were points of light, paying tribute to his patron. He didn't know they were worlds. He didn't know that one of them, Europa, was whispering a secret that would take 400 years to decode. He didn't know that the little point of light he was sketching in his notebook might be the second place in the universe where life took hold. The journey from his notebook to the Europa Clipper is one of the greatest intellectual adventures in human history. It is a journey that forces us to confront our own insignificance. If there is life in those oceans, it proves that we are not a miracle. It proves that life is a standard feature of the universe, as common as star formation or gravity. It means we are not special. And for some, that is terrifying. For others, like me, it is the most beautiful thought imaginable. It means we are not alone. It means the dark is not empty. So, let's peel back the ice. Let's look behind the curtain. Let's trace the clues that led us from the dry deserts of Mars to the wet, wild, and wonderful oceans of the outer solar system. It starts with the realization that our eyes deceived us. We judged a book by its cover. We saw white ice and thought death. But nature is a master of disguise. The white ice is not a tombstone. It is a cocoon. In the chapters to come, we are going to dive deep. Well, we're going to feel the radiation of Io, the volcanic hellscape that proves the power of tidal heating. We are going to fly through the plumes of Enceladus with Cassini, counting the seconds until impact. We are going to stand in the clean room with the engineers building the Clipper, knowing that the machine they are assembling will outlive them all. But first, we have to let go of the sun. We have to let go of the idea that warmth only comes from above. We have to embrace the cold. Because in the cold, in the dark, in the crushing depths, where no photon has ever reached, that is where the action is. The frozen curtain is rising, and what lies behind it might just change everything we think we know about what it means to be alive. Let's go. The story of the ice moons is, at its heart, a story of energy. Energy is the currency of the universe. On Earth, our economy is based on solar power. Plants capture sunlight. Animals eat plants. We eat animals. It's a solar economy. But the ice moons run on a different currency. They run on a gravitational economy. This is a crucial distinction because solar energy is fickle. It gets weaker the further you go. By the time you get to Jupiter, sunlight is 25 times weaker than on Earth. At Saturn, it's nearly 100 times weaker. If life depended on solar power, the outer solar system would indeed be dead. But gravity doesn't fade like light. Gravity is relentless. The grip of Jupiter on Europa is just as strong today as it was 4 billion years ago. This means that the energy source for these potential ecosystems is stable. It doesn't go out at night. It doesn't get blocked by clouds. It is a constant thrumming power source that can sustain a biosphere for eons. This stability is key. Life needs time. It took Earth billions of years to go from single-celled slime to complex animals. If the energy source flickered or died out, evolution would stop. But the tidal engines of Europa and Enceladus have been running since the birth of the solar system. They will keep running long after humans are gone. This changes the odds. When we calculate the Drake equation, the formula used to estimate the number of civilizations in the galaxy, We usually look for planets in the habitable zone of a star. But if moons can be habitable, the numbers explode. There are likely far more moons in the galaxy than there are planets. And if those moons can sustain life without being near a star, then the habitable zone is effectively the entire universe. We could be living in a galaxy that is absolutely teeming with life, but it's all hidden. It's all locked away in subsurface oceans, protected by ice, invisible to our telescopes. We could be looking right at a galaxy full of neighbors and not seeing them, because we are looking for radio waves and city lights while they are swimming in the dark, listening to the hum of their planet's core. This is why the frozen curtain metaphor is so powerful. It's not just a physical barrier of ice. It's a conceptual barrier. It's a curtain of ignorance that we are just now starting to pull back. The detective work that got us here is a testament to human stubbornness. Remember, we didn't go to Jupiter to find oceans. We went to study the gas giant. The discovery of the moon's secrets was a bonus, a happy accident born of curiosity. When Voyager flew by, the scientists could have just shrugged at the smooth surface of Europa. They could have said, "Weird ice," and moved on. But they didn't. They obsessed over it. They argued about it. They built models and simulations. They fought for funding to send Galileo. And when Galileo's high-gain antenna failed to deploy, crippling the mission's ability to send back data, they didn't give up. They rewrote the software of the probe from millions of miles away to compress the data, saving the mission and allowing us to discover the magnetic field. And when Cassini found the water plume at Enceladus, they didn't play it safe. They risked the spacecraft to get a taste. This is the human element of the story. The search for life is not a cold, calculated scientific endeavor. It is a passionate, desperate, high-stakes gamble. We want to know. We need to know. The drive to peek behind the curtain is hardwired into our DNA. As we move forward into this series, keep that paperclip in your mind. Feel the heat in the metal. Remember that the same force that burned your fingers is keeping an ocean liquid 500 million miles away. Remember that the universe is connected by these invisible forces. And remember that we are the only species on Earth capable of understanding this. The tube worms in the Pacific don't know about Europa. The bacteria in the ice don't know about Enceladus, but we do. We are the universe's way of exploring itself. We are standing at the edge of the greatest discovery of all time. The curtain is frozen. Yes, it is thick, and it is hard, and it is dangerous. But we have the tools to cut through it. We have the ships to reach it. And we have the will to ask the question. So, the next time you look up at Jupiter, shining like a bright star in the evening sky, don't just see a gas giant. See a mother hen, sitting on a clutch of eggs, keeping them warm in the cold dark of space. And imagine just for a second that inside one of those eggs, something is swimming, waiting for us to knock. The old maps are useless. The Goldilocks Zone is a myth. The real story is in the ice. And we are just getting started. How do you perform surgery on a ghost? That is the question that haunted the halls of the Jet Propulsion Laboratory for 20 years. It's a question that sounds like a riddle, but it was actually an engineering nightmare. We had looked at the night sky. We had spotted the mother hen of Jupiter, and we had focused on that second egg, Europa. But looking isn't touching. And in the business of space exploration, if you can't touch it, you can't prove it. We had a hunch. We had a suspicion that was keeping astronomers awake at night, whispering that the most profound secret in the solar system was hiding behind a mask of white ice. But how do you prove an ocean exists when it is locked beneath a crust as hard as granite and 5 times deeper than the Marianas Trench? How do you find water without seeing a drop? How do you peer inside a patient that is 400 million miles away without ever picking up a scalpel? The answer didn't come from a camera. It didn't come from a drill. It came from a whisper, a magnetic whisper that changed the way we understand our place in the cosmos. To understand how we heard it, we have to rewind the tape. We have to go back to the moment the mystery first presented itself, not as a solution, but as a problem. It's 1979. The Voyager 2 spacecraft is screaming through the Jovian system. It's a flyby mission, which means there are no second chances. You get one shot, one sequence of photos, as you hurtle past at tens of thousands of miles per hour. The team back on Earth is glued to the monitors, waiting for the images to decode line by line. They expect to see a dead world. That's what the textbook said. In 1979, the outer solar system was supposed to be a graveyard. We thought moons were just rocks or ice balls, frozen, cratered, battered relics, left over from the formation of the planets. We expected Europa to look like our own moon, gray, pockmarked, and utterly still. But when the image finally cleared on the screens, the room went silent. Europa didn't look like the moon. It didn't look like Mars. It looked like a cracked eggshell. It was bright, shockingly bright. In fact, we now know it's one of the most reflective surfaces in the entire solar system. But the real shock, Hugh, was what was missing. There were no craters. Now, you have to understand how weird that is. In space, everything gets hit. Callisto, Europa's neighbor, is one of the most heavily cratered objects we've ever seen. It looks like it's been shot with a shotgun for 4 billion years. But Europa was smooth. It was polished. It was crisscrossed with these long reddish-brown lines, scars that ran for thousands of miles. But there were no impact basins. In planetary science, craters are a clock. If a surface has a lot of craters, it's old. It has sat there gathering dust and impacts for eons. If a surface has no craters, it is young. It has been wiped clean. It has been resurfaced. Think about a skating rink. After a hockey game, the ice is cut up, rough, and scarred. That's Callisto. But then the Zamboni comes out. It lays down a layer of hot water, wiping the slate clean, leaving behind a perfect smooth mirror. Voyager showed us that something was acting as a Zamboni on Europa. The surface wasn't billions of years old. It was maybe only a few million. In geological time, that is yesterday. Something was erasing history. This was the first clue in our detective story. The ice wasn't a static shell. It was moving. It was cracking, shifting, and renewing itself. And the only way ice moves like that is if it's floating on something. If you look at the Arctic Ocean on Earth, you see ice flows crashing into each other, creating ridges and cracks because there is liquid water underneath, lubricating the movement. Voyager gave us the visual evidence. It told us this ice is slippery. But pictures can be deceiving. Maybe the ice was just warm slush. Maybe it was soft ice moving over hard rock. A photo can tell you what a surface looks like, but it cannot tell you what lies beneath. We needed to see inside the body. We needed a way to look through 10 miles of ice without landing. We had to wait nearly 20 years for the next clue. Enter the Galileo mission. This wasn't a flyby. This was an orbiter. It arrived at Jupiter in December 1995, ready to camp out and study the system in detail. Galileo was a masterpiece of engineering, but it was plagued by issues. Its main antenna failed to open, forcing it to send data back through a tiny backup antenna, trickling information like a dial-up modem in a world of broadband. But despite the slow data, Galileo had a superpower. It carried a magnetometer. A magnetometer is exactly what it sounds like, a device that measures magnetic fields. It's not a camera. It doesn't take selfies. It's a sensor that feels the invisible lines of force stretching through space. And this is where the story shifts from a visual mystery to a magnetic one. To understand what happened next, we need to talk about Jupiter. Jupiter isn't just a gas giant. It is a magnetic monster. It has the largest, most powerful magnetic field of any planet. If you could see Jupiter's magnetosphere with your naked eye from Earth, it would appear larger than the full moon in our sky. It is a colossal rotating bubble of charged particles and radiation, spinning around the planet like a lighthouse beam. As Jupiter spins, this massive magnetic field sweeps over its moons. It hits them with a wave of magnetic force every 10 hours. Now, usually, this doesn't matter much. If you wave a magnet over a rock, nothing happens. If you wave a magnet over a ball of ice, nothing happens. Magnetic fields pass right through non-conductive materials as if they aren't even there. So, the scientists expected the data from the Europa flybys to be boring. They expected Jupiter's magnetic field lines to pass straight through the moon, undisturbed, like wind blowing through a ghost. But that's not what happened. When Galileo swept past Europa, the magnetometer went haywire. The field lines didn't pass through straight. They bent. They warped. They were deflected around the moon. It was as if Europa was pushing back. It was creating a disturbance in the force. This is the part of the story where we have to stop and appreciate the human element. Data is just numbers until someone interprets it. And the person staring at those squiggly lines, the person who refused to dismiss them as a glitch, was a physicist named Margaret Kyvelson. Kyvelson was the principal investigator for the magnetometer. She saw this disturbance and realized something profound. The data looked weirdly familiar. It looked exactly like what happens when you try to push a magnetic field through an electrical conductor. Here is the physics, stripped of the jargon. If you take a magnetic field and change it rapidly around a conductor, like a copper wire, you induce an electric current in that wire. That electric current, in turn, generates its own magnetic field, a counter field that fights back against the original one. It's called Lenz's law. It's how induction stovetops work. It's how airport metal detectors work. When you walk through a metal detector, the machine creates a magnetic field. If you have a gun or a set of keys in your pocket, the metal conducts electricity, creates a counter field, and sets off the alarm. Margaret Kyvelson realized that Europa was setting off the alarm. Jupiter's spinning magnetic field was sweeping over Europa, and something inside Europa was conducting electricity so well that it was generating a counter-magnetic field. Europa wasn't just a rock, it was a battery. But here was the catch. Ice is a terrible conductor. Rock is a terrible conductor. So, what creates a global, uniform conductive shell around an entire moon? There is only one material common in the universe that fits the bill. It's not copper. It's not iron. It is salt water. Salty water conducts electricity beautifully. The dissolved salts, ions of sodium and chloride, allow the current to flow. Kyvelson looked at the data and realized the only model that fit the math was a global layer of salt water, sitting just beneath the ice, covering the entire moon. This was the aha moment. It was the planetary MRI. Think about an MRI scanner in a hospital. It uses a massive magnet to align the atoms in your body, allowing doctors to see your soft tissues without cutting you open. Margaret Kyvelson used Jupiter as the machine and Europa as the patient. By watching how the patient reacted to the magnetic field, she could see the blood flowing in its veins. She realized that Europa wasn't solid. It was a shell floating on an ocean, and not just a puddle. The magnetic data suggested this layer was deep, perhaps 60 miles deep. When you do the math on a sphere that size, the numbers become staggering. We are talking about a volume of water that is double that of all Earth's oceans combined. Think about that for a second. Take the Pacific, the Atlantic, the Indian, the Arctic, and the Southern Oceans. Drain them. Then fill them up again. Then fill them up again. That is how much water is hiding beneath the ice of this one tiny moon. It was a theory that revolutionized planetary science, but in the 1990s, it was still just a theory based on wiggles on a chart. And this brings us to a difficult truth about space exploration. I want to pause here and ask you something, because this is a dilemma that scientists face every single day. We live in a visual culture. We want to see things to believe them. If I told you there was a whale in your backyard, you'd want a photo. But if I showed you a graph of seismic vibrations and said, "Trust me, that wiggle is a whale," would you believe me? So, here is the question. Does indirect evidence satisfy you? If we never drill through the ice, if we never send a camera down to see the water, but the magnetic math is perfect, is that enough for you to say, we found an alien ocean? Or does it not count until we touch the water? I'm genuinely curious where you draw the line between theory and discovery. Let me know in the comments. Are you a show me the photo person or a trust the math person? Now, Margaret Kyvelson was definitely a trust the math person, but she knew she needed more than one pass to convince the world. A single flyby could be a fluke. Maybe Europa just happened to be passing through a weird pocket of plasma. So, she convinced the mission planners to do something risky. She wanted to use the remaining flybys to test the theory. If Europa really had an ocean conducting electricity, the direction of its magnetic field should flip as Jupiter rotates. Since Jupiter's magnetic axis is tilted, sometimes the field points up, sometimes it points down. If Europa is acting like a conductor, its induced field should respond to that orientation. It should wobble in perfect sync with Jupiter's rotation. It was a specific, falsifiable prediction. If the ocean was real, the magnetic north of Europa would shift position every 5.5 hours. If the ocean wasn't there, the field would be static or chaotic. Galileo swung by again, and again, and again. The data came back, and it was a perfect match. The magnetic signature danced in perfect rhythm with Jupiter. The math was undeniable. The ghost inside the machine was real. The Zamboni smoothing the surface was real. This was the moment the solar system changed for us. Before Kyvelson's magnetic detective work, the Goldilocks Zone was the law. We believed that to have liquid water, a planet had to be close enough to the sun to be warm, but far enough away not to boil. Earth was the standard. Everything else was too hot or too cold. But Europa is 5 times further from the sun than Earth. It is in the deep freeze. The surface temperature is minus 260 degrees Fahrenheit. By all rights, it should be a solid block of ice. But the magnetic whisper told us that the rules were wrong. It told us that you don't need sunlight to have an ocean. You need energy, yes, but that energy doesn't have to come from a star. It can come from gravity. It can come from the tidal dance we talked about in the last chapter, the stretching and squeezing of the moon's core. We realized that Europa is warm from the inside out. It's like a house with the windows boarded up, but a roaring fire in the basement. The implications of this are absolutely staggering. If you can have a liquid saltwater ocean this far from the sun, then the habitable zone isn't a narrow ring around a star. It's everywhere. It could be around Jupiter. It could be around Saturn. It could be around rogue planets drifting in the dark between the stars. Suddenly, the universe looked a lot wetter. But the mystery wasn't fully solved. We had the visual clue, the smooth ice. We had the magnetic clue, the induction. We knew there was water. We knew there was salt. But we were still missing a crucial piece of the puzzle. We didn't know if the ocean was alive. See, having water is great, but to have life, at least life as we know it, you need more than just water. You need chemistry. You need a mix of elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. You need energy sources. You need a way for the water to interact with rocks, to create complex molecules. On Earth, the deep ocean is alive because of hydrothermal vents. Cracks in the Earth's crust let water touch hot magma. The water superheats, dissolves minerals from the rock, and shoots back up like a chemical soup. That soup feeds bacteria, which feed tube worms, which feed crabs. It's an ecosystem that doesn't care about the sun. Does Europa have hydrothermal vents? The magnetic data suggests the ocean is in contact with a rocky mantle, which is promising. The reddish cracks on the surface suggest that stuff is bubbling up from below. Salts, maybe sulfates, maybe organics, and getting blasted by Jupiter's radiation, turning them red. But we couldn't see the vents. We couldn't taste the water. We were like doctors looking at that MRI. We could see the shape of the organs, but we couldn't take a biopsy. We were stuck on the outside looking in, tapping on the glass. And this is where the frustration sets in. We know it's there. We know it's huge. We know it has the potential to host life. But the ice shell is thick. Estimates range from 10 to 15 miles of solid ice. Drilling through that is a challenge we haven't even solved on Earth yet, let alone on a spacecraft with a delay of 45 minutes. Europa became the ultimate tease. A world that whispered, "I'm here," but kept its secrets locked behind a fortress of frozen armor. We had proven the ocean existed without ever seeing it, a triumph of intellect and deduction. But the desire to see, the primal human need to touch the water, remained unsatisfied. We needed a world that was less shy. We needed a world that didn't just hide its ocean, but flaunted it. We needed a world that didn't just whisper, but screamed. And while we were obsessing over Europa, staring at the magnetic charts and planning future drilling missions, another detective story was unfolding further out in the dark. Out at Saturn, 1 billion miles away, there was a tiny moon, a nothing moon. A moon so small, it barely qualified as a planetary body. It was just a bright speck of ice, dwarfed by the majesty of Titan. Nobody expected much from it. It wasn't on the priority list. It was supposed to be a cold, dead, frozen marble. But sometimes, the quietest suspects have the loudest secrets. While Europa was playing hard to get, keeping its ocean locked away in a vault, this tiny moon was preparing to do the unthinkable. It wasn't waiting for us to invent a drill. It wasn't waiting for us to build a better magnetometer. It was preparing to spit its ocean right into our faces. We had learned to read the magnetic whispers of Europa, and it taught us that the universe is full of hidden waters. But to truly understand what lies beneath, to taste the chemistry of an alien sea, we would need to leave Jupiter behind. We would need to travel to the Lord of the Rings. Because if Europa is the quiet, mysterious introvert, keeping a diary locked in a safe, Enceladus is the rebel standing on the roof, shouting its story to the stars. The magnetic whisper was just the beginning. The real noise and the real danger was waiting for us at Saturn. And this time, we wouldn't just look at the data. This time, we would drive a spaceship right through the spray. What keeps a heart beating inside a frozen corpse? It's a gruesome question, I know. But look at where we are. We are drifting in the deep freeze of the outer solar system, hundreds of millions of miles from the warmth of the sun. Out here, the laws of thermodynamics are cruel and absolute. Everything is supposed to cool down. Everything is supposed to settle. Energy dissipates, heat fades, and worlds die. By all rights, Jupiter and Saturn should be surrounded by graveyards, silent collections of rock and ice, frozen solid to their cores, drifting in a sleep that has lasted for billions of years. And for a long time, that is exactly what we thought they were. We looked at these moons through our early telescopes, and we saw stillness. We saw craters that looked like ancient scars, unhealed and unchanging. We saw white, featureless faces. We assumed that the drama of creation was over for these worlds. We assumed they were geological fossils, leftovers from the solar system's violent birth, now just quietly orbiting in the dark. But we were wrong. Somewhere in the darkness, something is keeping the lights on. Something is keeping the engines running. We found volcanoes erupting on Io. We found a shifting, cracking ice shell on Europa. We found geysers screaming out of Enceladus. These aren't dead worlds. They are alive. They are churning, breathing, and sweating heat into the vacuum. So, here is the mystery that kept astronomers up at night for decades. Where is the energy coming from? They are too small to hold on to the heat of their formation, like the Earth does. They are too far from the sun to feel its warmth. If you stood on the surface of Europa, the sun would look like just another bright star, offering about as much heat as a refrigerator light bulb in a warehouse. There is no fire here. There is no sunlight. Yet, the ice is melting. The rock is molten. The answer isn't in the chemistry. It isn't in the sunlight. The answer lies in a force we usually think of as the most boring, static thing in the universe. The answer is gravity. But not the gravity you learned about in high school physics, the kind that just holds your feet to the floor. No, this is gravity weaponized. This is gravity as an engine. To understand how a frozen moon can have a liquid ocean, you have to stop thinking about gravity as a pair of handcuffs holding a prisoner. You have to start thinking about it as a handsaw. I want you to try something with me. You don't have to stand up, but I want you to visualize this, or even do it, if you have one handy. Picture a thick metal wire, or better yet, a paperclip. Just a standard steel paperclip. If you take that paperclip and you hold it perfectly still, it's cold to the touch. It's room temperature. It's dead metal. But now, take it between your thumbs and forefingers. Bend it. Bend it back. Bend it forth again. Do it quickly. Keep going. Back and forth. Back and forth. Faster. You feel that resistance? That is the metal lattice fighting you. That is friction. Now, stop and touch the bend against your lip. It's hot. It burns. If you do it fast enough, you can actually blister your skin. You didn't hold a match to that paperclip. You didn't plug it into a wall socket. You created that heat purely through motion. You took mechanical energy, the movement of your hands, and you forced it into the metal structure of the clip. You created friction deep inside the atomic bonds of the wire. You turned movement into heat. Now, scale that up. Imagine the paperclip is the size of our moon. It's made of rock and ice and iron. And the hands bending it, that isn't you. That is Jupiter. Jupiter is a monster. It is more massive than all the other planets in our solar system combined. Its gravity well is so deep and so powerful that it dominates the space around it for millions of miles. If you are a moon orbiting Jupiter, you are not just floating in space. You are caught in a grip that makes a vice look like a gentle hug. But gravity alone doesn't create heat. If a moon orbited Jupiter in a perfect circle, nothing would happen. It would just sit there, frozen in the grip, like the paperclip before you started bending it. To get heat, you need the bend. You need the squeeze. This is where the dance begins. It's called orbital resonance, and it is the invisible heartbeat of the Galilean moons. Jupiter's major moons, Io, Europa, and Ganymede, don't just orbit at random speeds. They are locked in a precise rhythmic timing, a cosmic waltz conducted by gravity itself. For every 4 orbits Io makes, Europa makes exactly 2, and Ganymede makes exactly 1. It's a 4-2-1 resonance. It is perfect, mathematical, and relentless. Think of it like pushing a child on a swing. If you push at random times, the swing goes nowhere. But if you push at the exact right moment, every single time the swing comes back, you add energy. You go higher. You go faster. Because of this resonance, these moons line up with each other at regular intervals. Every time Io passes Europa, they tug on each other. Every time Europa passes Ganymede, they tug on each other. These gravitational nudges force the moons into elliptical orbits, ovals, not circles. And that is the key. That is the secret. Because the orbit is an oval, the moon's distance from Jupiter changes. Sometimes it's closer, sometimes it's farther away. When Europa swings close to Jupiter, the giant planet's gravity screams louder. It pulls harder. It physically stretches the moon, elongating it toward Jupiter like a football. Then, as Europa swings out to the far side of its orbit, the gravity weakens, and the moon snaps back into a sphere. Stretch, snap, stretch, snap. Every orbit, every few days, for billions of years. This is the paperclip. Jupiter is rapidly bending Europa, squeezing it like a stress ball. This constant kneading creates massive amounts of internal friction. Rock grinds against rock deep in the core. Ice grinds against ice in the crust. And just like the wire against your lip, that friction generates heat. This is tidal heating, and it changes everything we thought we knew about where life can exist. We used to think the Goldilocks Zone, that perfect distance from a star where water can be liquid, was a map of real estate. We thought you had to be close to the fire to stay warm. But tidal heating tells us that you can bring your own fire. You don't need a sun. If you have a Jupiter, gravity is a generator. It takes the cold kinetic energy of orbital motion and converts it into thermal energy, keeping the heart of the world molten and beating in the absolute zero of space. To see the raw, violent power of this engine, you don't look at Europa first. You look at its big brother, Io. Io is the innermost of the Galilean moons. It takes the brunt of the abuse. It is so close to Jupiter, and the resonance is so intense that the ground you would stand on rises and falls by 300 feet every single day. Imagine the entire surface of the Earth heaving up into the sky by the height of a skyscraper, then crashing back down every 42 hours. The result is hell. Io is the most volcanic world in the solar system. It looks like a moldy pizza, covered in sulfur yellows, reds, and blacks. It is literally turning itself inside out, spewing lava hundreds of miles into space. It is a world burning itself alive because it can't stop bending. But move one step out. Move to Europa. The grip is a little looser here. The bending is a little gentler. Instead of melting rock into lava, the tidal engine melts ice into water. This is the aha moment that defines our search for alien life. We realize that the ice shell we see on Europa isn't a solid block frozen down to the bedrock. It's a blanket. It's a lid. And underneath that lid, powered by the grinding of the core, is a global ocean of liquid water. It's not a pond. It's not a lake. It is a staggering amount of water, more than 2 times the volume of all Earth's oceans combined. Think about that. A moon the size of our own moon, holding twice as much water as Earth. And it's kept warm, not by sunlight, but by the rhythmic squeezing of gravity. This is the friction of Titans. This is the invisible engine. Before we head further out into the dark, I want to pause here for a second. I want you to check in with your own assumptions, because this stuff forces us to rewrite our internal dictionaries. Here is a question for you to chew on, and I'd love to see your take in the comments below. If life exists down there, swimming in the dark, warm waters of Europa, fueled by gravity instead of sunlight, would they even know the rest of the universe exists? To them, the 60 is a ceiling of solid ice, miles thick. They would have no stars, no sun, no concept of space. Their entire universe would be the ocean. So, here is the challenge. If we find them, do we tell them? Or is that the ultimate prime directive violation? Are we the aliens invading their perfect closed world? Let me know what you think. It's a wild thought experiment. Now, let's take that thought and travel nearly 1 billion miles deeper into the void. Because if you think Jupiter's engine is impressive, you haven't met the little engine that could. We are leaving the realm of the giant and heading to the Lord of the Rings. We are going to Saturn. If Europa is a masterpiece of hidden engineering, Enceladus is a magic trick. When we talk about Titans, we usually mean size. Jupiter is a Titan. Saturn is a Titan. Even Ganymede is a Titan, bigger than the planet Mercury. But Enceladus? Enceladus is tiny. It's laughable. It's barely 300 miles across. You could fit the entire moon comfortably inside the borders of Arizona. By every rule of planetary science, Enceladus should be a boring frozen ice cube. It's too small to hold heat. It has barely any gravity of its own. It reflects almost all the sunlight that hits it. It is the whitest, most reflective object in the solar system. It's basically a giant snowball. It should be the coldest, deadest place you can imagine. But when the Cassini spacecraft arrived at Saturn, it noticed something weird. Saturn has a ring called the E-ring. It's a faint, diffuse, ghostly ring. And unlike the other rings, which are made of ancient debris, the E-ring is made of microscopic ice particles that are constantly disappearing. Something has to be replenishing it. Something is spraying fresh ice into orbit around Saturn. The culprit was the tiny snowball. When Cassini swung its cameras toward Enceladus, it didn't find a dead world. It found a rebel. At the south pole of this tiny moon, the ice is ripped open. There are 4 massive parallel fractures, scars in the crust, that run for 80 miles. We call them the tiger stripes, and they are not cold. When we looked at them with thermal imaging, they lit up the screens. They were glowing with internal heat, radiating gigawatts of energy into the blackness. And from these cracks, Enceladus isn't just leaking, it is erupting. Massive jets of water vapor and ice particles are blasting out of the tiger stripes at 800 miles per hour, supersonic speeds. These plumes shoot so high that they escape the moon's weak gravity entirely and drift out to form the E-ring of Saturn. Enceladus is a moon that is actively spitting its ocean into space. But how? How does a moon the size of Arizona generate the power of a nuclear reactor? It's the same story, but with a twist. It's the friction of Titans again. Just like Europa dances with Io and Ganymede, Enceladus dances with a moon called Dione. For every 2 orbits Enceladus makes, Dione makes 1. That resonance keeps Enceladus's orbit eccentric. It keeps it oval. So, every time Enceladus dips close to Saturn, the ringed giant grabs it. But because Enceladus is so small and porous, it's actually quite fluffy density-wise. The tidal deformation is massive. Saturn needs this tiny moon, like a piece of dough. The friction concentrates at the South Pole. The ice shell flexes, cracks, and rubs together. The heat melts the ice below, creating a subsurface sea. And because the gravity is so low, that pressurized water finds the cracks, the tiger stripes, and blasts out into the vacuum. This discovery changed the game. With Europa, we have to drill through miles of ice to taste the water. We have to build a nuclear-powered cryobot, melt our way down, and hope we don't hit a rock. It's a mission that might not happen for 50 years. But Enceladus is giving it to us, for free. The samples are right there, floating in space. We don't need to drill. We don't need to land. We just need to fly through the cloud. And that is exactly what we did. But before we talk about the dive, before we talk about the taste of that alien spray, we need to appreciate the sheer scale of what this means. The paperclip analogy teaches us that energy is everywhere. For a long time, we thought life was fragile because it needed a star. We thought life was rare because it needed a Goldilocks orbit. We thought we were special because we had the sun. But tidal heating tells us that the universe is full of hidden engines. It tells us that you can have a liquid ocean in the darkest corners of the galaxy. It tells us that gravity, the force that holds the stars together, is also the force that cooks the soup of life. Enceladus pumps out roughly 15.8 gigawatts of heat power at its south pole. That is roughly the output of 20 nuclear power plants, generated entirely by the squeeze of Saturn. It is a testament to the power of friction. So, we have the heat, we have the water, we have the engine. The stage is set. The lights are on. The house is warm. The only question left is anyone home? To answer that, we have to look at what else is coming out of those vents. Water is great. Heat is great. But life needs more than a warm bath. It needs food. It needs ingredients. It needs a spark. When Cassini looked at the plumes of Enceladus, it didn't just see water. It saw complex organic molecules. It saw salts. It saw silica, tiny grains of sand that can only form when hot water touches rock, at temperatures near boiling. Do you know where else we see that specific cocktail of chemistry? We see it in the deepest trenches of the Earth's oceans. We see it at the Lost City hydrothermal vents in the Atlantic. We see it in places where the sun never shines, yet life teems in the darkness. Giant tube worms, ghost crabs, mats of bacteria that eat hydrogen and breathe iron. Enceladus isn't just a warm, wet rock. It is a chemical factory. The friction of Titans has created a reactor. Deep beneath that white reflective shell, the ocean is interacting with a rocky core. The water is leaching minerals from the stone. The tidal heat is cooking them together. It is a process called serpentinization, and it is the same process that many biologists believe started life on Earth. We are looking at a second Genesis engine, but knowing it's an engine and proving it's alive are two very different things. Cassini gave us a taste. It gave us a tease. It flew through the plumes and tasted salt and organics. But it wasn't built to find life. It was built to look at rings. It had a nose, but it didn't have a microscope. We were left with a tantalizing data set. We saw the smoke, but we couldn't find the fire. And this brings us back to the tragedy of Tantalus. We are so close. The water is splashing against our sensors. The evidence is literally raining down on the rings of Saturn. Yet, we are still just scraping the surface of the mystery. The friction of Titans has provided the conditions. It has melted the ice. It has stirred the pot. It has kept these worlds alive for billions of years, waiting for us to notice. But gravity can only do so much. It can create the stage, but it cannot create the actors. Or can it? If gravity provides the energy and the rock provides the chemistry, is biology the inevitable result? Is life just another way for the universe to dissipate energy? Just another form of friction? As we drift away from Saturn, leaving the glowing tiger stripes behind in the dark, we are left with a profound realization. The solar system is not a dead collection of rocks. It is a dynamic, grinding, heating, living machine. The paperclip is hot. The stress ball is squeezed. The oceans are liquid. And now, we have to ask the hardest question of all. We know the machine is running. We know the fuel is there. But what is the machine making? To find out, we have to stop looking at the physics and start looking at the biology. We have to stop looking at the moons as planets and start looking at them as petri dishes. We have to dive deeper than the sensors of Cassini could ever go. We have to talk about the ingredients of a soul. Because if the friction of titans can keep a heart beating in a corpse, maybe, just maybe, it can also wake it up. We've seen the engine. Now, let's look at the passengers. When we look at the plumes of Enceladus, we are seeing the exhaust of a potential ecosystem. But to understand what that ecosystem might look like, we don't need to invent sci-fi monsters. We don't need to imagine little green men. We just need to look in our own backyard. We need to look at the monsters that live in our own deep dark. Because the best map we have for the aliens of Enceladus isn't a star chart. It's a bathymetric chart of the Pacific Ocean. The friction that heats Enceladus is the same energy that powers the tectonic plates of Earth. It is the energy of movement. And on Earth, where that movement cracks the crust deep underwater, we find the vents. Black smokers, white smokers, chimneys of rockets spewing superheated mineral-rich water into the freezing crush of the abyss. For decades, biologists thought these places were wastelands, too hot, too toxic, too crushing. But when we went down there, we didn't find a desert. We found a jungle. We found life that doesn't care about the sun, life that doesn't care about photosynthesis, life that runs on chemosynthesis, eating the chemical energy of the Earth itself. If the friction of titans is doing its job on Enceladus, if it is cracking the core and heating the water, then those vents exist there too. The lost city isn't just in the Atlantic, it's on Enceladus. It's on Europa. And if the vents are there, the stage is not empty. So, as we stare at that tiny, bright, white dot in Saturn's rings, we aren't just looking at a moon. We are looking at a mirror. We are looking at a version of Earth that never left the deep ocean phase. A world where the whales never walked on land, where the birds never grew wings, where the eyes never evolved to see the stars. A world of eternal, warm darkness, cradled by the violent gravity of a gas giant. It is a haunting image, a lonely, thriving biosphere, locked under the ice, singing its songs to the crushing pressure, completely unaware that 1 billion miles away, a species of hairless apes is staring at their roof, wondering if they are home. The friction of titans keeps them warm, but it also keeps them trapped. Or does it? Remember the plumes. Remember the spray. Enceladus is the one world that breaks the seal. It is the one world that doesn't just keep its secrets, it shares them. The friction that melts the ice also breaks the ice. And in that violence, in that rupture, there is an invitation. We have accepted that invitation. We have built the ships. We have plotted the trajectories. We are done with just looking. The next chapter of this story isn't about gravity. It's about the hunt. It's about the specific, delicate, beautiful chemistry of life. It's about how we go from a warm paperclip to a living cell. We know the engine is running. We know the water is liquid. Now, we are going to find out what is swimming in it. The Titans have done their part. They have provided the spark. Now we go looking for the fire, because if we find it, if we find even one single microbe in that alien spray, then the friction of Titans didn't just warm a moon. It lit up the entire universe. It would mean that we are not a miracle. We are just what happens when you bend the paperclip long enough. And that is a thought that keeps you warm in the cold. So, we leave the gravitational dance. We leave the crushing grip of Jupiter and the rhythmic tug of Saturn. We have established the how. We know how the water survives. Now, we turn to the what. What is waiting in the dark? What kind of biology builds itself out of sulfur and hydrogen? What does a creature look like when it has never seen a photon of light? The physics is settled. The biology is the frontier. And the most terrifying, wonderful part, we might already have the data we need. It might be sitting on a server right now, buried in the noise, waiting for a clever eye to spot the pattern. The paperclip is hot. The ice is cracked. The ocean is calling. Let's dive in. Have you ever wondered why the things that have the most to say are often the ones we ignore the longest? Why is it that in the grand theater of the cosmos, the spotlight always seems to fall on the giants, while the true miracles are happening in the shadows, unnoticed, right beneath our noses? We spent centuries staring at the red spot of Jupiter. We spent decades obsessing over the rings of Saturn. We built entire mythologies around Mars because it looked like blood and war. But while we were looking at the monsters, a tiny frozen marble was screaming at us across the void, desperate to tell us that we were looking in all the wrong places. Welcome to the paradox of Enceladus. If you were drifting through the Saturnian system right now, floating in that silent, terrifying expanse between the rings, you might miss it entirely. It is shockingly small. We talk about moons like Ganymede or Titan as if they are planets in their own right, massive worlds with their own gravity and grandeur. But Enceladus is a speck. It is barely 300 miles across. To put that in a perspective that makes sense to our primate brains, you could fit the entire moon inside the borders of Arizona. If you drove from Tucson to the Grand Canyon, you'd have traversed the diameter of this entire world. It is a moon that has no business being anything other than a piece of orbital debris, a leftover icy crouton from the banquet that formed Saturn. And for a long time, that is exactly what we thought it was. When William Herschel first spotted it in 1789, he was pushing the technology of his time to its absolute breaking point. Through his 40-foot telescope, Enceladus was nothing more than a pinprick of light, a ghost haunting the glare of Saturn's rings. It was noted, catalogued, and then largely ignored. It was just another rock, a dead, frozen relic of the early solar system. And why wouldn't it be? Physics, as we understood it then, was a cruel accountant. Small things cool down fast. They lose their internal heat to the vacuum of space. They solidify. They die. By all the laws of thermodynamics, Enceladus should have been a solid block of ice, frozen to its core billions of years ago, silently tumbling through the dark. But Enceladus had a secret, and it hid that secret behind a mask of absolute perfection. This moon, too, is the most reflective object in our entire solar system. It has an albedo, a reflectivity score, of nearly 100%. If you were standing on its surface, without a visor coated in heavy gold, the sunlight reflecting off the ground would blind you instantly. It is whiter than fresh snow. It is whiter than a sheet of paper. It is pristine. And that beauty, that flawless, brilliant white, was the first clue we missed. Think about it. In space, things get dirty. Dust, micrometeoroids, radiation burns. Over millions of years, the surfaces of moons get darkened and scarred. Look at our own moon. It's gray, battered, and bruised. But Enceladus looks like it was minted yesterday. It looks brand new. For centuries, astronomers looked at that brightness and thought, how pretty. They should have been thinking, how is that possible? It wasn't until we sent a robot to check on the neighborhood that the mask began to slip. The year was 2005. The spacecraft was Cassini. It was a school bus-sized laboratory, a masterpiece of human engineering designed to explore the Saturnian system. Its main targets were the planet itself and the giant, hazy moon Titan. Enceladus was on the list, sure, but it was a flyover state. It was a box to be checked. We were going to do a couple of distant passes, take some photos for the textbooks, and move on to the more interesting targets. But as Cassini swung past this tiny Arizona-sized snowball, the instruments started screaming. It wasn't the cameras that caught it first. It was the magnetometer. This is an instrument designed to feel the magnetic field of Saturn, to sense the invisible web of energy surrounding the planet. As Cassini flew by Enceladus, the magnetic field lines bent. They warped. It was as if the moon was pushing back against Saturn, creating a disturbance in the force. That shouldn't happen with a dead rock. A dead rock is inert. It passes through the magnetic field like a ghost. But something around Enceladus was conductive. Something was interacting with the plasma environment. The scientists back at Jet Propulsion Laboratory scratched their heads. The readings looked like the signature of an atmosphere. But that was impossible. A moon this small doesn't have enough gravity to hold onto an atmosphere. The gas would just drift away into space in a matter of hours. Unless the atmosphere was being replenished. Unless something was pumping gas out from the interior faster than it could escape. The mission planners did something bold. They rewrote the script. They changed Cassini's trajectory. Instead of looking at Titan, they turned the robot's eyes back toward the tiny, bright moon. They told Cassini to look closer, and specifically, they told it to look at the South Pole. What they saw destroyed our understanding of the solar system forever. The images that came back didn't show a smooth, white surface. At the South Pole, the ice was shattered. There were 4 massive parallel fissures slashing across the landscape. They looked like claw marks, deep and jagged, running for 80 miles across the bottom of the world. The team named them the Tiger Stripes, but the visual shock was nothing compared to the thermal data. In the outer solar system, warm is a relative term. The surface of Enceladus usually hovers around minus 330 degrees Fahrenheit. It is a deep, bone-cracking cold. But when the thermal cameras scanned those tiger stripes, the sensors lit up like a Christmas tree. The cracks were glowing. They were radiating heat, gigawatts of it. And then, the cameras caught the silhouette. Backlit by the sun, spraying out from those tiger stripes, were massive, towering jets. Plumes of water vapor and ice crystals were shooting hundreds of miles into the black sky. This wasn't a dead rock. This was a cryovolcano. Enceladus was erupting. It was bleeding its insides out into the vacuum. This is the David versus Goliath moment of planetary science. You have Saturn, this gas giant, a tyrant of gravity, pushing and pulling everything in its orbit. And then you have this tiny, defiant moon. It's so small, it shouldn't even be active, yet it's putting on the biggest show in the system. It's pumping out so much material that it actually creates one of Saturn's rings. The E-ring, though, that faint, ghostly halo around the planet, that is made entirely of Enceladus's exhaust. This little moon is painting a ring around a giant. It defies every expectation. It challenges the very definition of where life could exist. We used to think you needed to be close to the sun to find water. We thought you needed a Goldilocks orbit. Not too hot, not too cold. Enceladus took the Goldilocks zone and threw it out the airlock. It proved that you don't need the sun to keep warm. You just need gravity. You need the friction of the dance. But here is where the story shifts from astronomy to something much more profound. We realized that we weren't just looking at water vapor. We were looking at an ocean. The way the moon wobbled as it orbited Saturn, a slight physical librations, proved that the ice shell wasn't frozen solid to the core. It was floating. There was a global layer of liquid water underneath that ice, sloshing around, disconnected from the rocky interior. And those plumes? That wasn't just steam. That was the ocean spray. Imagine the implications of that. On Europa, the ocean is trapped beneath 10 or 15 miles of concrete hard ice. To taste it, to sample it, we would have to land a spacecraft, drill through miles of cryo bedrock, and lower a submarine. It is a technological nightmare. It might take us 100 years to figure out how to do it. But Enceladus is the generous neighbor. Enceladus is the underdog that offers to share its lunch. It is literally shooting its ocean out into space for us. It is saying, here, you don't need a drill. You don't need a submarine. Just fly through the spray. Just open your mouth and taste it. So, we did. We are going to talk about that dive, the suicide dive, in just a moment, because it is one of the most heart-stopping maneuvers ever attempted in the history of spaceflight. But before we strap ourselves into the probe for that plunge, I want you to pause with me for a second. I want to ask you a question, and I want you to really think about it. Maybe even pause the video and type it out in the comments, because I read them all. Think about the times in your life when you found value in the place you least expected it. We are conditioned to look for the big things, the loud people, the flashy opportunities, the obvious paths. But Enceladus teaches us that the most profound discoveries often come from the quietest, smallest corners. Yes, here is my question to you. What is the Enceladus in your life? What is the small, overlooked thing, a hobby, a person, a quiet idea that turned out to be the source of your greatest energy or inspiration? What was your tiger stripe moment, where you realized the dead rock was actually alive? Let me know down below. I'm curious to see how many of us have found giants hiding in small packages. Now, let's get back to the edge of the ring. Let's get back to the dive. The year is 2015. The Cassini mission is nearing its end. The spacecraft is running low on fuel. The team knows that eventually they will have to destroy the probe to prevent it from accidentally crashing into Enceladus and contaminating it with Earth bacteria. But before they say goodbye, they decide to take one last, massive gamble. They order Cassini to dive directly through the plumes. This is not a simple drive-by. This is a bullet grazing the skin. They commanded the spacecraft to fly just 30 miles above the surface of the South Pole. That is lower than most satellites orbit Earth. At that altitude, and at the speeds Cassini was traveling, thousands of miles per hour, dust and ice particles aren't just snowflakes. They are shrapnel. If Cassini hit a piece of ice the size of a marble, the kinetic energy would be enough to blow a hole through the spacecraft. The mission would end instantly. The signal would just go dead. The tension in the control room was suffocating. You have to remember, the signal from Saturn takes over an hour to reach Earth. You can't joystick this. You can't react. You send the command and then you wait. You wait for an hour and a half of silence, knowing that the event has already happened. The spacecraft is either alive or dead, and you are just waiting for the ghost of the data to arrive. They sent the command. Go for the plunge. Cassini dropped its orbit. It screamed down toward the white, scarred landscape of the South Pole. It aligned its instruments. It opened its mouth, the cosmic dust analyzer, and the ion and neutral mass spectrometer. It flew straight into the fog. Imagine the view. You are hurtling over a landscape of fractured white ice, and suddenly you are engulfed in a towering curtain of mist. The sun flickers behind the vapor. The sensors are being pelted by millions of microscopic grains of ice. And then, it was over. Cassini punched out the other side, rose back into the black, and turned its antenna toward Earth. The data stream hit the deep space network. The screens in California lit up. Cassini had survived. It had tasted the spray. And when the chemists and the biologists looked at what Cassini had caught in its mouth, they didn't just see water. They saw the recipe for life. The plumes were 98% water vapor, yes. But the remaining 2%, that was the gold. They found salt, specifically sodium chloride, table salt. This told us that the water wasn't just melted ice. It had been in contact with rock. It had been leaching minerals from the core. They found methane. They found ammonia. They found molecular hydrogen. Now, if you aren't a chemist, molecular hydrogen might sound boring. But to an astrobiologist, that is the sound of a dinner bell. Molecular hydrogen is like a battery. It is a source of chemical energy. On Earth, there are microbes that live in the deepest, darkest parts of the ocean, far from the sun, and they eat hydrogen. They combine it with carbon dioxide to make methane. It's called methanogenesis. It is one of the oldest, most primitive forms of metabolism on our planet. And Cassini found all the ingredients for it, floating right there in the vacuum of space. But the data got even better. Years later, as they continued to comb through that data set. Because remember, the data is a library that we are still reading. They found something even heavier. They found large, complex organic molecules, carbon chains, the backbones of biology. We haven't found the fish yet. We haven't found the bacteria. But we have found the smoke. And where there is smoke, there is usually fire. Enceladus is showing us that its ocean isn't just a wet layer. It is a chemically active, heated reactor. The presence of tiny silica grains, nanoparticles of sand found in the plumes, was the final smoking gun. Those silica grains can only form in very specific conditions, hot water, around 190 degrees Fahrenheit, interacting with rock, and then cooling down rapidly. Do you know where we see that on Earth? Hydrothermal vents. The Lost City vents in the Atlantic Ocean. Places where towering chimneys of rock spew mineral-rich water into the cold sea. Places that are teeming with life. Tube worms, ghost crabs, blind shrimp, sprawling mats of bacteria. Ecosystems that don't care that the sun exists. Enceladus has those vents. We are almost certain of it. The tiger stripes are the exhaust pipes for a hydrothermal factory on the ocean floor. This changes the metaphor entirely. We aren't just looking at a David versus Goliath story of a small moon resisting a big planet. We are looking at a Noah's Ark. Think about the hostility of the universe. Space is a nightmare of radiation, vacuum, and cold. Jupiter is a radiation engine that fries electronics. Saturn is a gravity well that crushes comets. And yet, inside this tiny, unassuming shell of ice, wrapped in the dark, there is a warm, salty, organic soup that has been stewing for potentially billions of years. It is the ultimate underdog story because it suggests that life doesn't need a paradise. It doesn't need a blue sky and a yellow sun and a grassy field. It just needs a pocket of warmth and a little bit of chemistry. It suggests that life is stubborn, that it will hide in the cracks, that it will thrive in the places we dismiss as dead. The tiger's roar isn't a sound. There is no sound in space. The roar is the data. It is the sheer, undeniable volume of evidence that is shouting at us to come back. And that is the tragedy and the hope of our current moment. Cassini is gone. We crashed it into Saturn in 2017 to protect the very moon we are talking about. We didn't want to risk a dead spacecraft contaminating an ocean that might have life. So, we sacrificed the messenger to save the message. Now, Enceladus spins alone again. The plumes are still erupting. The tiger's stripes are still glowing. Every second, gallons of water and organics are being thrown into the void, freezing into snow, and coating the surface in that blinding, perfect white. It is waiting for us. We know the address. We know the door is unlocked. We know dinner is on the table. We just have to build the ship to go back and sit down. But as we look at Enceladus, we have to wonder if this tiny, overlooked speck can hold the potential for a second Genesis. What else have we missed? If the smallest moon has the biggest secret, what about the quietest stars? What about the empty spaces between the galaxies? We have learned that we cannot judge a book by its cover, especially when that cover is a shell of ice 3 miles thick. The roar of the tiger's stripes has woken us up. It has shifted our gaze from the star above to the oceans below. It has taught us that the universe is not just a place of physics and fire. It is a place of water and salt. And as we prepare to leave the Saturnian system in our narrative, as we prepare to look at the broader implications of these ocean worlds, we have to carry this lesson with us. The lesson of the underdog. The lesson that the most important things are often hidden in plain sight, waiting for someone brave enough to fly through the spray. We have tasted the water. We know the potential. The physics of the paperclip has given us a warm ocean. The chemistry of the vents has given us the menu for life. But a menu is not a meal, and a recipe is not a cook. To find the cook, to find the thing that might be swimming in that dark, warm water, we have to go deeper. We have to move from the where and the what to the who. Because if Enceladus is roaring, the question that keeps me up at night is simple. Is anything roaring back? Is the silence of the cosmos actually filled with the whispers of 1 trillion microbes hidden in the shells of 1 billion icy moons, waiting for us to tune our ears to the right frequency? We've seen the stage. We've seen the props. Now, we need to meet the actors. And to do that, we have to understand not just the moons, but the water itself. We have to understand what it means for a liquid to be the cradle of existence. We have to look at Earth not as the standard, but as the anomaly. Enceladus has shown us the door. Now, we have to walk through it, because the tiger is loose, and it's calling us home. Let's follow the sound. But let's bring it back to the visual. I want to leave you with one final image of this chapter before we move on. I want you to imagine standing on the surface of Enceladus, near the South Pole. You are in a spacesuit, obviously. The ground beneath your boots is not solid rock. It is snow. Fine, powdery alien snow. It is the fallout from the plumes falling back down to the surface in slow motion thanks to the low gravity. You look up. Saturn dominates the sky, a massive golden arc, sliced in half by the razor-thin line of the rings. It is terrifyingly beautiful. And then, the ground shudders. Not an earthquake, but a deep, resonant vibration. Ahead of you, a mile away, the ice splits. A curtain of white fire, geysers of crystal and gas, erupts silently into the black. It rises up, 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 until it joins the ring that encircles the sky. You are standing on a world that is bleeding into the heavens. You are standing on a world that is trying to tell you something. It is saying, I am here. I am warm. And I am waiting. There are plans. There are concepts, robots that look like snakes, designed to slither down the tiger stripes, probes that can land and melt their way through the ice. We are dreaming up the next generation of explorers, inspired by the little moon that could. But until those machines are built, until they launch, until they arrive, we have the data, we have the mystery, and we have the profound, shaking realization that the universe is far more creative than we are. We thought we knew the rules. Enceladus broke them all. And in the wreckage of those rules, in the shattered assumptions of what a moon should be, we found the most precious thing of all, possibility. Pure, unadulterated, freezing cold, boiling hot possibility. So, as we close the book on the tiger's roar, remember this: the universe does not hide its secrets because it hates us. It hides them because it wants us to grow. It wants us to build the telescope. It wants us to fly the probe. It wants us to dive through the plume. It wants us to earn the answer. And Enceladus is the teacher that gives us the hardest test, but whispers the answer when we aren't looking. The answer is water. The answer is heat. The answer is life. Now, let's turn the page. Let's take this possibility and see where else it leads. Because if Enceladus is the underdog, then there is another moon out there that is the heavyweight champion. A moon that makes Enceladus look like a test run. We are going to Jupiter. We are going to the king. And we are going to meet the moon that started it all. The ice is thicker there. The radiation is deadlier. The stakes are higher. But the promise is exactly the same. The paperclip is bent. The tiger has roared. And the hunt is on. If life arises twice within a single solar system, completely independently, does that mean life is not a miracle, but a machine? That is the question that keeps me up at night. It is the question that sits at the center of the dark, cold void we are about to enter. We are leaving the spray of Enceladus behind. We are leaving the underdog. We are firing our thrusters and turning the ship toward the giant. We are going to the place where the radiation sings a song of death, and the ice hides a secret twice as big as all of Earth's oceans combined. We are going to Europa. But before we get there, before we look through the eyes of the Galileo probe, or watch the Europa Clipper unfold its solar wings, we have to stop looking up. We have to stop looking at the stars. To understand what is waiting for us at Jupiter, we have to look down. We have to look into the deepest, darkest, most crushing pressure cooker on our own planet. We have to talk about the day we discovered that we are not alone on Earth. For the longest time, biology had a golden rule. It was a rule that felt more like a law of physics. It said that the sun is the father of all things. Every blade of grass, every plankton, every cow, every human. We are all just bottled sunlight. The sun gives energy to the plants. The plants feed the animals feed us. If you turn off the sun, the chain breaks and the lights go out. Life, we believed, was a solar phenomenon. This belief defined our search for aliens for centuries. We looked for the Goldilocks Zone. We looked for planets that were not too hot, not too cold, but just right, places where the sun could touch the water. We ignored the outer dark. We ignored the ice. We thought of the outer solar system as a graveyard, a place where the sun was too weak to nurture a single cell. But in 1977, we got a wake-up call. And it didn't come from a telescope. It came from a submarine. Geologists, not biologists, mind you, but geologists, were dragging a sensor package deep into the Pacific Ocean, near the Galapagos Rift. They were looking for heat. They were looking for the seams of the world, the places where the tectonic plates pull apart and bleed magma into the sea. They were hunting for hydrothermal vents. Now, you have to understand the expectation here. At 8,000 feet down, the pressure is crushing. It is pitch black. The water is near freezing. There is absolutely no sunlight. According to the golden rule of biology, this should be a desert, a wasteland. Maybe, just maybe, you'd find a stray, confused fish or the slow drift of marine snow, the dead organic matter falling from the sunlit world above. But mostly, it should be rock and water and death. The submersible, named Alvin, went down into the dark. The pilots turned on the floodlights. They drifted toward the vents, expecting to see bare basalt and shimmering heat. Instead, they saw a garden. It was an explosion of life. It was a jungle in the abyss. There were giant tube worms, 6 feet tall, with blood-red tips waving in the current, like fields of alien corn. There were ghostly white crabs scrambling over the rocks. There were clams the size of dinner plates. There were shrimp swarming so thick, they looked like a blizzard. The scientists in the sub were stunned. They were literally speechless. This wasn't just a surprise. It was a violation of the rules. There was no sun here. There hadn't been sunlight here for millions of years. So, where was the energy coming from? How were these things alive? They realized as they sampled the water that they were looking at a completely different operating system for life. These creatures didn't care about the sun. They didn't need it. They were feeding on the planet itself. The vents were spewing out superheated water, rich in minerals, sulfides, hydrogen, methane. Nasty stuff. Poison. To us. But for the bacteria coating those rocks, it was lunch. They were performing chemosynthesis. They were taking the chemical energy from the Earth's heat and turning it into sugar, into food, into life. The tube worms had no mouths and no stomachs. They were just farming these bacteria inside their bodies. This was the moment everything changed. We realized that life isn't a solar phenomenon. Life is a planetary phenomenon. It doesn't need a star to shine on it. It just needs a heat source and water. It needs a battery. And that brings us back to the vacuum of space. That brings us back to the king. If you look at Jupiter through a backyard telescope, it's beautiful, it's striped, it's stormy, it's grand. But if you look at it with the eyes of a physicist, Jupiter is a bully. It is so massive that it doesn't just hold its moons in orbit, it tortures them. We talked about this with Enceladus, but at Jupiter, the scale is terrifying. Europa is caught in a gravitational tug-of-war. On one side, you have Jupiter, the 800-pound gorilla, pulling with immense force. On the other side, you have Ganymede and Io, the sibling moons, yanking back in a rhythmic dance called orbital resonance. Poor Europa is in the middle. Every few days it gets stretched. Then it gets squeezed. Stretched. Squeezed. Do this with me. If you're sitting at a desk, grab a paperclip, or just imagine one. If you take that paperclip and bend it back and forth rapidly, what happens? It doesn't just break. It gets hot. You can feel the heat in your fingertips. That is friction. That is energy being converted from motion into heat. Now, imagine the paperclip is a moon the size of our own moon. Imagine the hand bending it is the gravity of the largest planet in the solar system. That friction doesn't just warm the rock, it melts it. It creates a furnace inside the core of the moon. And that heat has to go somewhere. It radiates outward, up toward the surface. But Europa is wrapped in a shell of ice, hard as granite, frozen by the vacuum of space. So, you have fire below and ice above. And where fire meets ice, you get water. For decades, this was just a theory. We looked at Europa through the grainy lenses of Voyager, in 1979. And we saw something weird. We saw a cue ball. The rest of the solar system is pockmarked with craters. Look at our moon. Look at Mars. Look at Callisto. They are scarred by billions of years of asteroid impacts. They look like battlefields. But Europa is smooth. It's bright. It's covered in lines and cracks that look like the veins in a bloodshot eye. But there are almost no craters. In planetary science, a smooth face means a young face. It means something is erasing the scars. It means the surface is being recycled. It looked like ice that was floating on something, moving, cracking, healing. Then came the Galileo mission. In the 1990s, and this is where the story turns into a detective thriller. The Galileo probe wasn't equipped to see an ocean. It didn't have a sonar. It couldn't land. It just had a magnetometer, a compass basically. Margaret Keevelson, a brilliant physicist, was watching the magnetic field data as Galileo swung past Europa. She noticed something that shouldn't be there. Jupiter has a massive magnetic field, the biggest thing in the solar system. As Europa flies through it, something weird happens. The magnetic field bends. It gets diverted. Margaret realized that Europa was acting like a giant electrical conductor. It was generating its own induced magnetic field to fight back against Jupiter's. Rock doesn't do that. Ice doesn't do that. Do you know what does? Salt water, a global spherical shell of salty water acting like a giant wire, conducting the electricity of Jupiter's magnetosphere. The math was undeniable. The only way to explain the signal was an ocean, and not just a puddle. Based on the data, we calculate that Europa's ocean is about 60 miles deep. Compare that to Earth. The Mariana Trench, the deepest point on our planet, is only 7 miles down. Europa's ocean is so vast that it holds twice as much liquid water as all of Earth's oceans, rivers, and lakes combined. Think about that. The Earth is the water planet, right? We are the blue marble. But we are actually a desert compared to Europa. We are a dry rock with a thin, damp coating. Europa is the real water world. So, the stage is set. We have the water. We have the heat from the tidal squeeze. And thanks to the chaos terrain, those jumbled, broken blocks of ice on the surface, we think the ocean interacts with the surface. Radiation from Jupiter bombards the ice, creating oxidants, creating chemical fuel. The ice churns, and that fuel might be sinking down into the dark, down to the bottom, down to the rock. And this is where the metaphor of the Alvin submarine becomes more than just a story. It becomes a blueprint. If we could shrink ourselves down, put on a pressure suit that could withstand the weight of 60 miles of water, and stand on the seafloor of Europa, what would we see? We wouldn't see sunlight. We would be in total, crushing darkness. But we might not be blind. We might see a glow, a faint, ghostly light in the distance. We would walk toward it, fighting the currents, and we would feel the water getting warmer. We would smell, if we could smell, the sulfur. And there, rising out of the alien rock, we might see them, the black smokers, the hydrothermal vents of Europa, chimneys of stone spewing superheated mineral-rich water into the freezing ocean. And around them, this is the question. This is the second Genesis. Would we see two worms? Probably not. Evolution plays by the same rules, but it doesn't repeat the same shapes. But would we see life? Would we see mats of bacteria clinging to the rock, eating the chemical soup? Would we see swimming things, blind and pale, navigating the thermal currents? If we found a single microbe there, just one, it changes everything. You see, when we look for life on Mars, we are looking for a lost cousin. Mars and Earth exchanged rocks billions of years ago. It's possible that life started on Mars and came to Earth on a meteorite, or vice versa. Finding life on Mars would be incredible, but it might just mean we are related. It might be the same Genesis. But Europa is sealed. It has been under that ice for billions of years. If life started there, in that dark ocean, it started independently. It had nothing to do with us. It had nothing to do with Earth. And if life happened twice, in one solar system, around one star, then life is not a miracle. It is a cosmic imperative. It means that wherever you have water and heat and rock, life must emerge. It means the universe is a life factory. It means that when we look up at the night sky, at those billions of stars, we aren't looking at a lonely void. We are looking at a crowded room. But we haven't seen it yet. We haven't tasted the water. This is the tragedy of Tantalus. We know the water is there. We know the heating is there. We can see the salts staining the cracks on the surface, painted in rusty reds and browns. But the ice is thick. 10 miles, 15 miles. We don't know for sure. We can't just dive through the plumes like we did at Enceladus. Europa does spit out plumes, we think, but they are sporadic. They are shy. To get to this ocean, we have to be smarter. We have to be patient. That is why we build the Clipper. NASA's Europa Clipper is not just a spacecraft. It is a promise we made to ourselves. It is the largest planetary probe ever built by NASA. It has solar panels the size of a basketball court because it has to catch the weak, dying sunlight out there at Jupiter. It is armored like a tank because Jupiter's radiation belts are like a buzzsaw of subatomic particles that fry electronics in hours. Clipper isn't going to land. It's going to orbit Jupiter and perform flyby after flyby, swooping low over the ice, tasting the thin atmosphere, using radar to look through the ice shell. It is going to map the ocean. It is going to tell us how thick the wall is. It is going to look for the hot spots. It is the scout. It is the first ship of the fleet. Because if Clipper tells us what we think it will tell us, if it confirms that the ocean is reachable, that the chemistry is right, then the next mission won't just fly by. The next mission will land. The next mission will melt. The next mission will swim. We are already designing them. Cryobots, nuclear-powered needles that sit on the surface, heat up, and melt their way down, unspooling a communication wire behind them, like a robotic spider. Down, 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 through miles of ice, until they break through, until the camera turns on, until the spotlight cuts through the eternal black. Imagine that moment. Imagine the feed coming back to Earth. It will take almost an hour for the signal to cross the void. Billions of people watching a screen, waiting for the data to arrive. The screen flickers, the static clears. We see the black water, we see the vent, and then something moves. It sounds like science fiction, but the math says it's real. The geology says it's real. The only thing missing is the visual. We are standing on the edge of a philosophical cliff. We have spent our entire history as a species believing we are special, that we are the chosen ones, that the Earth is the only stage where the play is being performed. But the curtains are opening on a second stage. The lights are coming up, and the set design looks hauntingly familiar. The black smokers of the Atlantic are not just a curiosity. They are a prophecy. They are telling us that life is tougher, stranger, and more stubborn than we ever dared to dream. They are telling us that the sun is a luxury, not a necessity. We used to fear the dark. We populated it with monsters. But now we know the truth. The dark is not empty. The dark is a cradle. As we drift away from Europa In our imagination, watching that cracked white marble recede into the blackness of space, I want you to feel the weight of that ocean. Feel the pressure. Feel the cold. But also, feel the hope. We are not looking for little green men. We are not looking for civilizations. We are looking for a second Genesis. We are looking for proof that the universe is alive. And we are so close. The paperclip is bent. The ocean is waiting. The ships are launching. I want to leave you with a thought that might change the way you look at the night sky tonight. We often ask, are we alone? It's the ultimate question. But I think we might be asking it wrong. If we find life in the dark of Europa, deeper than our own oceans, older than our own mountains, independent of our own sun, does it make us less special? Or does it mean that we are finally, truly, part of a family? What do you think? If we find a microbe on Europa, does it kill God? Or does it reveal a bigger one? Does it make you feel insignificant? Or does it make you feel connected? I want to hear your answer. Not the scientific one, the human one. Go down to the comments and tell me. If the universe is a factory for life, what is our job in it? If you want to join this expedition, if you want to be on deck, when we finally break the ice, make sure you're subscribed. Ring the bell. We have a long way to go, and the outer solar system is just getting started. Next time, we leave the ice behind. We're going to a world that looks like Earth, but acts like hell. A world of methane rain and plastic sand. We are going to Titan. But for now, keep looking up, and don't forget to look down. I'll see you in the dark.